Hey everybody, welcome back to the shop. I'm Jarrell at Jarrell Education. Today, I'm going over another classic physics problem for like a first year physics student or AP physics student. This problem combines inclined plane with a pulley. Now in this example I have no friction. In the next video I'll do one with friction. If you like this video and it helps you, please like and subscribe to the channel to let me know that I'm doing the right thing. Okay, let's get into it. Okay, we're doing another classic problem from physics. We have an inclined plane with a mass on it, but this time we've got a pulley and another mass hanging, so let's read it. Masses of 6 and 8 kilograms are placed on an inclined plane and connected with a string as shown below. The incline has negligible friction with the 8 kilogram mass and the pulley is massless. Find the acceleration of the system and the tension in the string, and we're letting g, the acceleration due to gravity, be 10. Alright, so let's get into this. As far as the mass on the ramp goes, we know that we have a downward force, and we know that that's equal to mg, which in this case is going to be 80. Now, if you haven't seen my video on the inclined plane problem, go back and watch that before you attempt this, because it's going to explain a lot of things I'm not going to re-explain with breaking up the vectors, okay? So that's already there. Just go back and check that out, and then come right back here. Now, I also have force normal in that direction, okay? So we'll call that Fn. And then there's also a tension pulling this mass up the ramp. So we'll call that T, okay? Now what I'm going to do is I'm going to break this up into, well, I'm going to draw a set of axes on here first that's tilted with that because it's going to accelerate either up or down the ramp. And this angle right here is the same thing as the 30-degree right there, so I know that that's 30. We don't need to break up force normal and we don't need to break up tension, but we do need to break up that mg vector because it doesn't fall on an axis. So let's do that. And again, if you haven't seen my video on how to do this, just go back and look at the inclined plane problem because it explains a lot. This vertical component is going to be mg cosine of 30, which turns out to be 69.3. And this other component here, keep in mind, this is really like just a rectangle that we're drawing, right? We're finding two sides of it, basically. That's the same as this, and that's going to be opposite the 30. So that one's 80 sine of 30, which turns out to be 40. Okay, now, if I just look at this, I'm going to appeal to Newton's laws right now. So let's take the y direction first. So the summation of all the forces in the y direction is equal to m times the acceleration in the y direction, which we know is 0 in this case. So I can say force normal minus 69.3 is equal to 8 times 0, which is just 0. So I know that force normal is equal to 69.3 newtons. Now, in this problem, that doesn't really matter much, and I didn't ask for it. That's going to come up when friction is involved, as I explained in the inclined plane video before. Okay, so right now I found it. That's great. Okay, we're just going to put that on the side. I can say this. The summation of all the forces in the x direction is equal to m times a in the x direction. Okay, but before I actually fill that out, let's go over to the 6 kilogram mass and put in what its forces are. So I've got down is going to be 60 newtons, mg. Up is going to be a tension force. Okay, now keep in mind that the tension forces are the same, and the only reason that's true is because I said in the problem that the pulley was massless. Later on when we do rotational stuff, okay, the pulley's not going to be massless anymore and those tensions won't be the same. But for now, since the pulley's massless, it's not taking anything away from the system. We can just sort of neglect it and say that the tensions are the same. Okay, since on the ramp the force pulling, the component of gravity pulling it down the ramp is 40, and there's no friction to contend with, okay? And then the driving force, the one that's pulling on everything, is 60. I know this thing is going to accelerate up the ramp, and I know the 6 kilogram mass is going to accelerate down. So like I said before in a previous video, since the 6 kilogram mass is going to accelerate down, I'm going to make down the positive direction. So for the 6 kilogram mass, it's going to be the summation of all the forces, and I guess I can say in the y direction, because it's moving up and down, is equal to the mass times the acceleration in the y direction. So here's what we got. We're going to have 60 minus t is equal to 6a. You know, we can, now I just want to point out too, this acceleration and this acceleration are going to be the same since the two masses are connected by a string. Okay? So now right here I have an equation. That's great, but it's got two unknowns, so that means I got to go back to my other equation and start filling things in now. And now that I know it's going to accelerate up the ramp, I'm going to make up the ramp the positive direction. So it's going to be that equation for the forces in that direction is going to be t minus 40 is equal to 8a. And again, I've got another equation with two unknowns. So now I'm going to take these two equations and I'm going to solve them separately. So let me scroll up a little bit. And we're right. T minus 40 equals 8a. That's this one. And then negative t plus 60 is equal to 6a. Now notice I didn't change this equation at all. I just wrote it down there, but I just put the t in the front to make it obvious that that's going to add out when I add the equations together. So that's gone, and I get 20 is equal to 14a. So now when I divide both sides by 14, what I'm going to get is a is going to be equal to 1.43. And the unit would be meters per second squared. So I've solved for a. Now I can take a and I'm just going to plug it back into this equation, and now I'm going to solve for t. So I'll do that over here. T minus 40 is equal to 8 times 1.43. And that means that t minus 40 is going to be equal to 11.43. Then I add 40 to both sides and I get the tension is equal to 51.43 newtons. Okay? Now, I just want to point one or two things out here. The tension in the string is 51, so it's less than 60. Now, if this mass right here had just been hanging and it wasn't accelerating in any kind of way, just hanging by a string, the tension would be 60. But since it's accelerating down, it does make sense that the tension in the string is actually less than what the weight would be normally.